Hello, scholars. So today I'm going to talk to you about the Shapiro and Wilk test, the Shapiro Wilk test of normality, and how to use it in JASP and how to interpret it. Okay, so we can check for normality by looking at a histogram, which we'll do in a moment, or we can test for it. There's a statistical test. There's actually more than one you can choose from. The Shapiro Wilk test is great for smaller sample sizes. Some people say around 50. I usually select it less than 200 in a sample size. The null hypothesis, meaning, there's nothing going on here. The null hypothesis states that the distribution is normal. You need to know that, but I'll teach you more about hypothesis testing later. Okay, so in a Shapiro-Wilk test, I can literally order a statistical test and interpret the results for a clear black and white answer. Okay, the reason we often want to test for normality is that lots of statistical tests will assume a normal distribution. So you always look before you run that test if there's a violation of normality, because the assumption of normality is not met, we might select a different test. Okay, so let me show you first how to run the test in JASP. Okay, so what we want to do to run our test, we are running to see if our entire variable, so not by group, but the whole variable itself is normally distributed. Okay, so today we're testing aptitude and leadership. So I'm going to move them over to this variable side. So I went to descriptive statistics. Okay, so remember it's analyses, descriptive statistics. And I'm going to come down here, and for the sake of other work, I'm going to order a few of these other things so I can talk to you about it in a minute. Right here under distribution is our Shapiro-Wilk test. I'm going to click it, and it's going to show up in my descriptive statistics here. I can see my sample size for 64 for each of them. None of them are missing. We got our mean, median, and mode, standard deviation, skewness, and kurtosis. Here is our Shapiro-Wilk test for each of these. And let me show you where it's easier to see. Okay, so I have highlighted this first part, Shapiro-Wilk. This is the actual test statistic. If we calculated this by hand, this is the number we'd get for aptitude and then for leadership. The p-value right here is what we're going to interpret. Okay, P stands for probability. Probability of committing a type 1 error. In social sciences, we set that at 0.05. I will teach you more about that in a different video on hypothesis testing. Okay. The hypothesis for a normality test is that the null hypothesis is that the data is normally distributed. There's nothing going on. It's normally distributed. That's what we expected to find. So if P is greater than 0.05, my alpha, the data is normal. JASP will automatically be set at 0.05 for you. All right. If P is less than 0.05, there's a significance. The data is not normal. Okay. So My p-value of my Shapiro Wilk for aptitude is 0.548. That is greater than 0.05. P is greater than 0.05. My data is normal. So for leadership, P is 0.169. The data is greater than, P is greater than 0.05. The data is normal. But what if I'd had a p-value of 0.03? Well, then P would be less than 0.05 and the data is not normal and the assumption would be violated. So this is how you report this in APA. See, I've got my W. Most statistical symbols are italicized. I report my test statistic and I report my p-value and I always refer to my table. And I state whether or not the assumption is met. So a Shapiro Wilk test of normality, there's more than one normality test, so I identify which one I used, showed that leadership was normal. W equals 0.973. P equals 0.169. The assumption of normality is met. Okay. Now, I also want to show you how to check using a histogram or other graphs. So we're going to do this on aptitude. Now, we already know that aptitude is normally distributed, but I want to talk for a minute about interpreting it and how I might report that. Okay, so I can go to JASP and I can order my histogram. And remember, I can do that right here under descriptives. I would simply scroll down to plots. Basic and customizable are typically what I use. I want a distribution plot and I put the density, that's the line. Okay, I can order my QQ plot, which I'm going to show you how to interpret here as well. And it'll take a minute to pop up. And I can also order a box plot, which I'm going to show you how to do. And look, if I have outliers, I always hit label them. Okay, so let's talk about it. Here's my aptitude histogram, right? And we can see it seems to be approximately normal. Well, I expected that because we ran the test. Okay, but let's look at a few things. Let's see. My median is slightly higher than my mean. And if you think back to my variance video, I had said that when the median was higher than the mean, we could have a slight positive skew. I'm sorry, when the median is higher than the mean, it's a slight negative skew. Excuse me. Okay. So I can also look at these numbers, skewness. There's slightly positive. Kurtosis, there's hardly any kurtosis there. So how might I report that? Let's go back to our paper. Using an inspection of a histogram, aptitude appeared to be approximately normal, with the median being slightly higher than the mean, on a slight positive skew of 0.66, with negligible kurtosis. Remember, I got that right here, right? And kurtosis was almost 0. And if you remember my other video, JASP sets it at 0 instead of 3 like others. Okay, now how else could I inspect? I can inspect for normality using a QQ plot. By the way, I hate QQ plots. But understanding the QQ plot, the red line represents the expected values if the sample was perfect. And the data, we want the data points to closely follow the red line to be approximately normal. Now, if the data starts to curve away at the tails, it suggests a skewness. If there's clusters of data away from the line, like several data points, the tails are heavy, which means that it's also, there's high kurtosis going on. And if it hugs the line mostly throughout, it's approximately normal. Now, let's say I have my points curve away from the line, but it goes above the line. Well, that's what I have. Mine go above the line here. So that means that I have a right skewed distribution or a positive skew. If these points were below the line, I'd have a negative skew. But this is slight. This all follows the line closely, so I'd still say approximately normal. If I had lots of data points on either end, I'd say that we had kurtosis violated, heavy tails, right? Now there's one other thing we can look at here. We can look at a box plot. Oftentimes I'll inspect a box plot to determine if there's outliers. Now we have the edge of the box. This is an edge down here at 2. This is an edge here right above 5. This is the first quartile. This is the fourth quartile. This is the interquartile range, and that heavy line is the mean. And that's second and third quartiles, which is where the bulk of the data falls or should fall. Okay. When I have a circle outside of the box, it's an outlier or a point outside of the box. But is it a significant outlier? Significant usually is defined by being greater than 1.5 steps from the edge of the box. Because when it's significant, it can cause my data to skew, or it can cause normality to violate. So I look at that. This is not greater than 1.5 steps from the edge of the box. If it were, it would be above a 6. Okay, when we look at that. But there's one other thing you can do here. We can label our outliers in JASP, so you can go back and look at that case to see if there's an issue. Okay, so I can go back to my box plot and I can hit label outliers. And if there's an outlier, it'll tell me which case number is the problem. Now see, leadership had no outliers, but aptitude had 1, and it was case number 12. Why do I want to know that? Well, the first thing I want to do is check and see if my data is accurate, right? So I can go back and I can look at my data either by going here or clicking on these little side arrows, right? And I can find case number 12. Well, there's case number 12. It's going to let me click on it. There we go. So I've highlighted case number 12, and I'm looking for aptitude. Well, his score was 5.7287, right? That's a little bit above everybody else, but I have no concern that this might be an error. But if I had a number like 33 when everybody else is between 1 and 6, I'd better go back and see if there's a data entry error for my data. Okay. I could also check other things like, was there a mistake in my sampling technique? For example, I did a study once where I was asking if there was a relationship between the number of hours spent emailing a week and other things. Okay. And most of the people emailed, the number of hours they spent a week emailing were between 1 and 5 hours. I had 3 people that spent more than 40 hours a week at it. That indicates to me that maybe emailing was part of their job. Why would somebody spend all that time every week? 40 hours a week is a job. So in this case, I might have a problem with my sampling, a mistake in my sampling. So I would go back and I would say personal time spent emailing, not for job. And that might have changed their numbers. Okay, so we look at outliers for more than one reason. Now, if I wanted to report this outlier, right, I would just simply state that a box plot was inspected for outliers and there were no significant outliers greater than 1.5 steps away from the box. And then remember, I always want to refer to my figure for APA. So let's look at that APA figure 2. Notice that's bolded and the name of the figure is italicized. Figure 3, here's figure 4. And I called it box plot of aptitude. By the way, that works the same way for tables. Notice how I formatted my table in APA 2. Table 2, Shapiro Wilk, and I refer to the table within my paper. Okay, if you have any questions, please reach out to me.